Hey guys, in this video we will discuss enzyme kinetics, particularly the Michaelis-Menten approach. Enzyme kinetics is one of the oldest methods to understanding enzyme mechanisms. It aims to determine the rate of a reaction and how it changes in response to changes in experimental parameters. Michaelis-Menten enzyme kinetics relates the rate of enzymatic reactions with the substrate concentration. Biochemical reactions with a single substrate typically follow Michaelis-Menten kinetics, which is why it is so important that we study this topic. The outcomes of this video is that you will be able to understand the parameters and terms of Michaelis-Menten kinetics as well as its assumptions. You will also be able to interpret Michaelis-Menten plots as well as Lineweaver-Burk plots. We will also show you how a Michaelis-Menten plot can be made experimentally. The Michaelis-Menten model for kinetics presumes a simple two-step reaction as shown here. In the first step, the enzyme binds to the substrate, and in the second step, the substrate is converted to a product and released. Do you notice anything about the above reaction? Well, there's not a K-2 associated with the second step of the reaction. In fact, there are several assumptions associated with Michaelis-Menten kinetics. The first is that there is no product present at the beginning of the kinetic analysis, so we can ignore the reverse reaction of E plus P going to ES. Furthermore, the first step of the reaction, or the binding step, is very fast, while the catalytic step is much slower. This implies that the second step is rate limiting and determines the overall rate of the reaction. Another assumption is that the rate of formation of ES is equal to the rate of its breakdown. Therefore, the initial rate of the reaction is in a steady state where the concentration of ES is constant. This is also called the steady state assumption. The final assumption is that the concentration of S is much larger than the concentration of E. This is because the enzyme is a catalyst and thus can be recycled. So a large amount is not needed for the reaction. Furthermore, we can assume that the amount of S bound to E is much smaller than the amount of free S. This means the amount of S is constant throughout the reaction. On the other hand, the total amount of E exists in two forms, bound to the substrate ES or free E. Thus, the total enzyme concentration is the sum of the concentrations of ES and E.
The assumptions mentioned allow us to successfully derive the Michaelis-Menten equation shown here. The Michaelis-Menten equation relates initial velocity, V0, maximum velocity, Vmax, and the initial substrate concentration, S. The Michaelis constant, or Km, is equivalent to substrate concentration S, at which the initial velocity, V0, is 1/2 of the maximum velocity. Go through the following tutorial portion to learn how to derive Km equals S when V0 equals 1/2 Vmax. First, substitute 1/2 Vmax for V0 in the equation above. What do you get? You should have gotten 1/2 Vmax equals Vmax times the concentration of the substrate over Km plus the concentration of the substrate. The next step is to then multiply both sides by the denominator. What do you end up with? You should have gotten 1/2 Vmax times Km plus the substrate concentration equals Vmax times the substrate concentration. The third step is to expand the equation. You should get 1/2 Vmax times Km plus 1/2 Vmax times the substrate concentration equals Vmax times the substrate concentration. The fourth step is to subtract the term containing the substrate concentration from the left-hand side of the equation. What do you end up with? It should be 1/2 Vmax times Km equals 1/2 Vmax times the substrate concentration. The final step is to cancel out the common variables between both of the sides of the equation. What are you left with? You should be left with Km equals the substrate concentration. You have now proven that at 1/2 Vmax equals V0, Km equals the substrate concentration. This can be observed in the graph below, and Km is defined by the number of steps of the reaction and the relative rates of the steps.
Now we're going to actually talk about the Lineweaver-Burke plot. The Lineweaver-Burke equation creates a double reciprocal plot that allows us, as students, to more easily visualize enzyme kinetics. It is a plot that yields a straight line so that it can be used to accurately determine Vmax and Km. And this discrepancy in accuracy can be seen in the comparison of the two plots shown here. The plot on the left shows the standard Michaelis-Menten plot, while on the right shows the transformed Lineweaver-Burke plot. As seen by the two graphs, the plot from the Michaelis-Menten equation can only give approximations of Vmax and Km, which can vary amongst individuals, whereas these values can be more accurately determined from the double reciprocal plot by simply calculating the x-intercept and y-intercept. However, it should be noticed that although the Michaelis-Menten plot by inspection gives less precise info, computer-assisted nonlinear regression works very well. Values are more accurate than Lineweaver-Burke plots because small errors in data propagate to larger error via linear regression. In order to transform the Michaelis-Menten equation into the Lineweaver-Burke equation, take the reciprocal of both sides. So the first line of this equation shows the standard Michaelis-Menten equation. The next step is to take the reciprocal of both sides. And this simply means flipping the fraction. The next step is to separate the components of the numerator. And the final step is to simplify. And the simplified final step is therefore the transformed Lineweaver-Burke equation. The final equation is comparable to the standard equation for a linear regression, y equals mx plus b, in which 1 over v naught is y and 1 over the concentration of substrate is x. Negative 1 over km is the x-intercept, 1 over v max is the y-intercept, and the slope is km over v max. It is important to remember that once these values are calculated from the equations, the reciprocal must then be taken in order to obtain the actual values for v max and km.
We mentioned earlier that Km is a measure of how much substrate concentration is needed to reach the Vmax. Do you remember what the K negative 1 over K1 also meant? Right, the Kd. So the Km equals Kd. However, this is not always the case for most enzymes. For reactions with several steps, the kcat is equivalent to the rate constant for the limiting step. This kcat comes from the Vmax over the total enzyme in the reaction and represents the number of substrate molecules converted to product in a given time for a single enzyme, which is also referred to as the turnover number. Another way to think about catalytic efficiency is as a specificity constant of a certain enzyme under certain conditions. It may seem like these variables and values come from the book, but you really can experimentally derive the catalytic efficiency of an enzyme and then create a Michaelis-Menten plot. The images to the left show an enzyme kinematics experiment using absorbance to measure the amount of product in solution.